Next, we consider the other way that you can connect components in a circuit, and that is by connecting them in parallel. So when components are connected in parallel, there's actually multiple paths for the current to flow through. So first of all, the first thing that defines components connected in parallel is that each of the components, so here I have 3 light bulbs, they are each connected on both sides. There is a connection to the battery. So for example, here's one onto the battery. The wire comes out, it gets to this junction, and it's connected to the middle bulb, it's connected to the other bulb, and it's connected to the other bulb, right? So all 3 bulbs are connected on one end to the battery, and then the other end of the battery comes around and it connects to the switches. But if you ignore the switches, then it's also connected to the other end of the bulb. So it's like a ladder, right? These look like they are the rings of a ladder, and then they're connected in the same way to the battery. And of course, here's another picture, another example. So here's my battery, comes out, here's the wire, and it connects to each of the light bulbs on either side, and on the other side it connects to each one, although there is a switch here. So one of the things that you should notice in this particular picture is that when you have bulbs that are connected in parallel, if one of the bulbs is disconnected, like in this case with a switch, the other bulbs still stay lit, and that's because they are independently still connected to the battery. So I can make a connection that goes from the battery up to this bulb in the middle, goes through the filament, comes out, and then goes back. We're looking at the electron flow. So we can look at the Phet simulation again, and we can answer a few questions. So let's answer the questions first, and then we'll go back and we'll look at the Phet simulation. So how does the voltage across each of the components in the parallel circuit lab with these bulbs compare? So for this parallel circuit, what is the voltage across each of these components? And it turns out the voltage across each of the components in parallel is exactly the same. And not only is it the same, but it's the same as the battery. So if I measure the voltage across the battery, I measure the voltage across this bulb, or I measure the voltage across that bulb, the voltages will all be exactly the same as the battery. How does the current through each of the bulbs compare to one another and to the current that comes out of the voltage supply? So if we consider Ohm's law, V equals IR, or the current is the voltage over the resistance, each of these bulbs has the same voltage. So they have the same V, the voltage V, but they may be different resistance values. So the resistance of one bulb might be bigger than another bulb, and so that means that the current through each of the components may be different. Each component has the same voltage, but may have a different amount of resistance. The current that flows through the components are not the same as the battery. So what happens is the current through the components has to add up to the current from the battery. So if the current through the first bulb was 1 amp and the current through the second bulb was 1 amp, that means the current that's coming out of the battery here would have to be 2 amps, right? So it has to add up. So current comes out of here, it splits up between these bulbs. Some of it goes one direction, some of it goes the other direction, but it has to be equal. What happens to the brightness of the bulbs when you add additional bulbs? Of course, the brightness of the bulbs is related to the current. So if the bulbs dim, this means the current has decreased. If they become brighter, it means it increases. And it turns out that the bulbs, as you add additional bulbs in parallel, the brightness of the bulbs stays the same. So the same current, each one of those bulbs is still connected independent to the voltage supply. So they're always going to get the same current flowing through them, and if the current is the same, the brightness is the same. What happens to the current that's coming from the battery as additional bulbs are added? And the answer is the current coming from the battery increases, and the overall resistance in the circuit decreases. So this is a harder concept, but the idea is that as you add additional bulbs, each bulb is going to draw current. And as you draw more current has to come out of the battery. Overall current in the circuit is inversely proportional to the overall resistance. So if you add more bulbs and the current from the battery goes up, the overall resistance has to go down. So let's look at the Phet simulation again. So here's our Phet simulation, And I have this one set up so that I have 3 bulbs that are connected in parallel with one another, and I actually have switches through all of these. Well, not the one, but the other 2 I have switches. So the first thing that we could look at is what happens to, well, let's plug them all in, right? So how do the brightness of the bulbs compare? They're all about the same brightness, right? And that's because they all are identical bulbs. So these all, see the resistance down here is 10 ohms. So 10 ohms and 10 ohms. So let's look at the current that goes through each of the bulbs. So the current through the first bulb is 2 amps. The current through the second bulb is 2 amps. The current through the third bulb is 2 amps. And so 2 plus 2 plus 2 is 6. If I look at the current that's coming out of the battery, it's 6 amps. So when components are connected in parallel, the current that flows through the components when you add them together has to be equal to the current that comes out of the battery. All right, let's check the voltage. So here's my voltmeter. There's not a lot of space here. Let's do this. Let's put this back for now. Here's my voltmeter, and I'm going to put it across the battery. And I have this battery set for 20 volts, so it's reading 20 volts across the battery. In parallel, the voltage across the bulbs is the same as the battery. So the first bulb is 20 volts. The second bulb is 20 volts. And the third bulb is 20 volts, right? So components connected in parallel all have the same voltage, and that voltage is the same as the battery. If you disconnect one of the bulbs in the circuit, the other bulbs stay lit with the same brightness. So if I disconnect them, they are still the same brightness. It's kind of hard to see that in the circuit, but if I go back and I measure the current, it's still 2 amps. So the brightness would be the same and still 2 amps here. And of course now the current that's coming out of the battery is 4 amps, right? Because they have to add together. I can disconnect this one, right? And now 2 amps and 2 amps. So independently these bulbs are connected to the battery. So adding additional bulbs increases the current through the battery, but the current through each of the bulbs stays the same. Now each of these bulbs had the same current, and that's because of the fact that they had the same resistance. But if I change the resistance of this bulb to 20, change that, and I close the switch, and I close this switch. The top bulb no longer has the same current going through it. Now it only has 1 amp, where both of the other bulbs, which are only 10 ohms, get 2 amps, right? But 2 plus 2 plus 1 is going to give me 5. So if I change the resistance of one of the bulbs, the voltage across them stays the same, right? So this is still going to be 20 volts because it's connected to the battery. The top one is still going to be 20 volts because they're in parallel, but the current has changed because I changed the resistance. So bulbs connected in parallel always have to have the same voltage, but they don't have to have the same current if they are not identical bulbs. I think we've answered most of those questions with the simulation. If not, you can certainly go back and play with the simulation yourself. So we'd like to be able to solve problems. So similar to a series circuit, if you have a parallel circuit which has components that are connected in parallel to a battery, we can replace this circuit with an equivalent circuit with some total equivalent resistance connected to the battery. We want to approach this problem different than we would a series circuit. So let's think about how we would do that. So here we have 2 bulbs that are connected in parallel to one another. One bulb has a resistance of 20 ohms, one has a resistance of 40 ohms, and they're connected. This is supposed to say parallel, not series. That was a copy and paste error. So this is not series, this is parallel to a 10-volt battery. And we want to fill in the table below. So the very first thing that we realize is that they are connected in parallel. And when components are connected in parallel, the voltage across all the components in parallel is the same. Since we know our battery voltage is 10 volts, that means that we also know the voltage across each of the bulbs also has to be 10 volts. So the starting point for parallel circuits is to realize that all of the voltages are going to be the same. Next, we can use Ohm's law to find the current in each of the bulbs. So we know the voltage across each of the bulbs and we know the resistance, so we should be able to find the current. So the current through bulb 1 is just the voltage across that bulb over the resistance. The voltage is 10 volts. The resistance of that bulb is 20 ohms. 10 over 20 is 0.5 amps. I can do the same thing for bulb 2. So bulb 2 is 40 ohms. So the voltage is 10 volts. The resistance is 40 ohms. So 10 divided by 40 is 0.25, and so I know the current through bulb 2 is half of what the current through bulb 1 is because it has twice the resistance. Next, I'd like to figure out how much current is coming out of the battery. The current that's coming out of the battery is the sum of the current through all the components that are connected in parallel. Again, this should say parallel. So if I want to find the total current, I would add the current through the bulbs together. 0.5 plus 0.25 tells me that the current through the battery, coming out of the battery, has to be 0.75. Again, we haven't talked about power here, but we'll do that later, and we'll come back and we'll fill that in at a later time. I'm going to go back for 1 second. Now, you'll notice that I never had to use this equivalent circuit here. And so that's okay. So when we have a parallel circuit, we really don't need to use an equivalent circuit because of the fact that we know the voltage is already across those components, and so we can find the current and we can solve for it that way. I did want to point out, and it's not on this slide, that the total resistance here is actually smaller than the resistance values of 20 and 40 because the current that's coming out of this battery here is 0.75. And so there's a voltage of 10 volts, 0.75 amps coming out, so that resistance has to be smaller than the original resistance in the circuit. So as you add bulbs in parallel, the current that comes out of the battery increases, but that total equivalent resistance actually decreases. One of the things I always like to do, because students sometimes struggle with series and parallel circuits, is to do an analogy. So there's a toll road analogy. So a series circuit is like a single toll lane every mile. So suppose that you're on your way to the beach and there's one lane of traffic. There's not multiple lanes, it's one lane of traffic. And you encounter a toll and you have to pay the toll and then you continue. So a series circuit would be, suppose that you pay the first toll, but then 2 miles later there's another toll on that line, and then 2 miles later there's another toll. Every time you hit a toll, you're going to slow down. And so there's all these cars, there's only one lane, and they all have to keep stop and paying the toll. So as you add additional tolls, it's like adding additional bulbs. And as you add additional tolls, you're slowing down the traffic. So more tolls causes a decrease in the current flow or the flow of the traffic and more resistance to the flow of the traffic. Parallel, on the other hand, is a situation where you're on your way to the beach and suppose there's lots of lanes, right? So you're at the toll road where you have to pay to get across the bridge, and there's a number of different toll lanes. Well, maybe there's only 3 toll lanes open at one given time, and then and there's quite a lot of traffic, but all of a sudden they decide to open 3 more. So they're adding 3 more parallel toll lanes. All of a sudden there's more lanes opened, so there's more, the traffic that can flow faster through those tolls. So that's an example of parallel. So as you add additional lanes in parallel, you have more flow. The cars can go more quickly, and that's the same thing as adding additional bulbs in parallel. That means that more current is going to come out of the battery to fill those, to go through those bulbs. So just as a sort of summary, if you have components that are connected in series, components in series will always have the same current flowing through them, but the voltage across the different components is going to split so that all of the current through those components adds up to the voltage of the battery. If one of the components is disconnected from the circuit, that causes all of the devices to stop. In parallel devices, all of the components have the same amount of voltage, and that's the same voltage as the battery. On the other hand, the current that comes out of the battery has to split between the different components that are connected in parallel, but if you add the currents up, they have to add up to the current that's coming out of the battery. If one component is broken, like the switch example in the parallel circuit, the other ones still stay. It does not cause the other ones to go out, right? They still stay lit. So we could ask, how are our homes wired? And the answer is parallel. So if something happens to one of your electrical outlets, it doesn't cause every single light, every single plug in your whole house to go out. It's just that one component. And we could also ask the question, have you ever blown a fuse or a circuit breaker in your home? If you've ever blown a circuit breaker, and we're going to talk a little bit more about this, you can go back and it causes a number of components in your house to go out, but you go back and you just flip the switch and it causes the current to go back on. So a number of devices can be connected to a particular circuit breaker. So I didn't really say what a fuse was, but as more devices are connected to a circuit in parallel, it causes more current to be drawn. So remember, our house is connected in parallel. Now, not everything is connected to the same circuit breaker, but a number of different outlets or lights or components or whatever are connected to a particular circuit breaker. So suppose that we had one circuit breaker that was connecting a number of outlets, and we connected a lamp to it, and that lamp draws 2 amps of current. And then we had a heater because it's really cold, and we draw 10 amps, and then we decide to use our toaster, which draws 8 amps. We actually have 20 amps coming out of there, right? Because they're connected in parallel and I add them all together. So maybe I have a circuit breaker in my house that's a 20 amp circuit breaker. And what that does is it does not allow more than 20 amps to be drawn to that particular section of the house. So if I were to connect something else to that particular line of that circuit breaker, it would cause that circuit breaker to flip, and then I'd have to turn off some things, and then I'd have to go back and flip the switch. So I've had situations in my house where maybe I'm running my vacuum cleaner and I had it connected to the same outlet as like my toaster or something like that, and you can actually cause those circuit breakers to flip. Safety fuses are not used nearly as often in houses, but basically a safety fuse is a little different than a circuit breaker. Once the safety fuse is broken, then you have to put a new fuse in. So basically what's going on is if you have a fuse in the circuit, it might look something like this. And there's a wire inside that fuse that when too much current flows through it, it melts the wire, and if it exceeds the current, and then that fuse is actually in series with the power supply and then all those components. So if that fuse were to break or melt, then the power can no longer get to those particular components. So the fuse is put in series with the supply line to prevent overloading of the circuits. Most modern buildings don't have fuses anymore. Some components do have fuses in them. Like if you use a voltmeter, there's a fuse in there because there's a battery and so on. I live in an old house. When we first moved into the house, our water heater actually had a fuse. We changed that so we don't have to worry about it anymore. Circuit breakers are more common, and I sort of mentioned those. Those use electromagnetic induction, and they can be reset. We're going to talk about electromagnetic induction later.